Do you have your Flickr link? If you need your Flickr link, please let me know. This is today's attendance question. It is a curl calculation. So let's try. I'll let you try to find the curl of the vector field. It was a full question in section 14.6. So by now, I think we should be able to calculate the curl. I think you can try your process calculating cross product. It's similar to a cross product calculation, but instead of multiplying, we'll be a second name operator. Okay, so you already have the answer for the curl of the 15 minutes to calculate them. So we're going to identify the question from the calculation. I mean, we have to know how to calculate curl in order to complete section 14.6. Let's try to write it organized way. To calculate curl, we have to have the partial derivative operator. The x, the y, partial differentiation with respect to the zero. Okay, then we're gonna have our vector, the vector filters. And identify the x times sine of x plus y. First component, second component is x times y. The last component is yz plus x. So that's the vector. If you're calculating the curl of f, it's also going to be a vector. This is a vector. So what do we calculate? We will combine, cross, combine, and subtract. So these two combine is going to find the partial derivative of this vector, of this function with respect to the y variable, and you can say you're going to get a differentiating y, you get one times z, so that's v. And then subtract, this how we subtract the differentiation of this with respect to the z. And there's no z in this function, so this differentiation gives us the 0. So we're minus 0. All right, and that's the first component. The second component is we combine this column with this column because there's something in the middle. So we move it. Oh. Right. We move the last column to right next to the first column right next to the last column. Sure, I'll be the right thing. And x sine x plus 1. Right, and move right next to it just so they can also combine and subtract. This is a positive diagonal, this is a negative diagonal. The positive diagonal has no z, so that's 0. Differentiation with respect to 0 minus this differentiation with respect to the x, we get 1, -1. Last component is these two. See, that's pretty much kind of like what we were doing when we were doing cross product calculation. We differentiate this function with respect to the x variable, which then gives you a y. Now, this differentiation with respect to the y variable, you get 1, so it's 1 minus 1. So that's the curl function. But we're calculating the curl function evaluate at this point. So now we're going to calculate this, this factor that we just did. But you would evaluate it with pi 0, 2. So the evaluation of giving was 2, the 2. The middle is -1, it doesn't change. The last one was y minus 1, y was 0. Okay. We don't see any x's in this representation of the curls. First one being a pi has really no visible impact on the calculations. That's the final answer. I hope that you are able to identify the right factor for the curl. Okay. So the final answer should be a vector 2, -1, -1, 2, -1, -1. It will be. I hope that with more and more practice, we get better at understanding curl. Feel free to read about it.
I'll learn catch the calculation.
Okay. In class, we really focus on just the mathematical part of it. But curl and divergence have their own physical meaning in relation to any vector field. So there has the understanding part of it, we didn't focus on them, but that doesn't mean they're not important. If you read about it, you might have to do similar calculation or similar understanding in physics or other classes. So, but at least with practice, we need to know how to figure out the theory. Okay. Go back to the page.
I see.
Anyone else? Everybody else? It should be B if you're still hesitating. It's 2i -j -k. So it's B. So we use the ijk to identify the three direction. X direction, we multiply with I vector. I is a unit vector along the positive x-axis. J is a unit vector along the positive y-axis. K is a unit vector along the z direction, the axis. All right. So far, this is all the solution that we have collected. Do you have any homework question you need to ask? Any questions? Are we doing okay so far? Brian, do you have any questions?
Not right now.
Question. Let me try again. If you haven't submitted your answer yet, maybe I should let the scanner stay on. So then during the class session, if you figure out your answer, you can enter them. This is a first question. It was B. You should know that occasionally we have more than one clicker question because I realized that occasionally people leave early and didn't do the other clicker question because you were either not paying attention or left early. So that's the first question that we practice. If nobody let me know, say bonus point for completing the homework. Yes, on the final exam, if you did bring your homework on paper or any writing, so you have written homework either on paper or on any devices, I'll give extra credit as well. Because one way or the other, I do promote us try to write presentation of our solution. I mean, any written presentation is more, it leaves a longer track in our brain. And also it leave a track, a paper track as well. Later, if you have to do any calculus work, these are the kind of things you can fall back on. So I do feel like we will get out of the class, get more stuff out of class if we have a habit of writing about. It may end up in your closet or it may in your story forever. You will never use your calculus stuff, but you may end up somehow help you out when you're doing some work in graduate school, which is what happened to me. So all my past notes, some of them was just sitting there, but some of them I really reread them over and over to help me understand stuff. Any other questions? All right, if there's no question, no other question, we may end up doing more practice question. But this is our first one. If you are you figuring out? I see that you just log into our Clicker. This is a solution that we calculated. It's a calculation of Pearl. Scanner is still on if you want to enter your answer. I'll have the Clicker scanner on if you want to enter your answer. In the meantime, let's look at a couple of questions on the homework site. I realize the question that we did is the question about Stokes theorem, but we focused on the calculation of Pearl rather than the Stokes theorem. But in our homework, we heavily related to the later a few questions are all about Stokes theorem. And we have to know how to do it. The question I put up on the practice question for the final exam, you can see how it's selected. I pick out this question. Okay, that was one question we already done. It's a homework question number 9 or number 11. Let's try to compare. It is question 9. So we talked about the solution for question 9 yesterday, so assume that you should be okay. Other than that, if you are stuck on any homework question for chapter 14, I mentioned that I did provide the homework solution on church review. It's under HW homework solution folder. You can find out 14.2, 14.3, 4, 5, 6. The solutions all in there. You can compare your version with this version. Of course, the homework solution will be one single version. Every student have a different version of the homework. So even if you read the solution, it will not be identical. You kind of have to understand the reasoning and go back to your version. But at least you won't be in the dark. You will be knowing some example, some process of the calculation. Right. So other than that, I'm going to show how to calculate question 10 and question. I explained 11 yesterday, so maybe we should talk about 10 and 12. So this is the last question on the Stokes. You guys already have done this assignment. It was a question of using those theorem to calculate the circulation along the square of side 7, center at the origin, lying in a y plane in order to do counterclockwise when viewed from the positive axis. The wording is kind of interesting. It's explained that whether the rotation is counterclockwise or clockwise. It depends on how you look at it. Because it's three-dimensional, if you look at from the front, it's counterclockwise. If you look at from the back, it might be clockwise. So the perspective is kind of, it's very clear which side are we looking at. So anyway, let's look at how we do this question. We did bring a couple of examples of Stokes theorem. This is the last question on 14.6. Hopefully, the more we do it, the better we understand, both with understanding on how to calculate Pearl and also understanding on how do we apply Stokes theorem to ease the calculation burden. Now, this question says we're doing, this is a line integral, it's a circulation of vector field, which typically is calculated with the line integral. According to Stokes theorem, it equal to a double integral. A surface integral, I should clarify, surface integral is not the same as double integral, but surface integral will be calculated eventually using a double integral. Double integral is a calculation method, but surface integral is a special question. So according to Stokes theorem, this is equal to curl of the vector f dot dots NCS. So that's the Cardinal theorem. If we, that's the Stokes theorem. If we try to follow this, we can actually do it both ways. If you prefer, you can identify the line representing a square of size 7 center at the origin in the YZ plane. You can calculate the line integral on the fourth side of the square and add it together. I suspect it won't be too hard to do because it's a square. But we're going to follow the calculation of the Stokes theorem and calculate the double integral on the other side. So let's first calculate the curl of the vector. In order to do that, first we will identify our vector field. It's x, y for the first component, z for the second component. You can start working on your version of this question. It's the last question on 14.6. So maybe we have better understanding of the differences in similarity between your version and my version. Also, you might finish this faster if you do it together. Even if you did it halfway, it would probably save you some time later. Okay, so the calculation for the curl, we do cross combine and subtract. So curl of G, we have a vector G here, is equal to the first component differentiating the 6y with respect to the y variable. Combining these two, then we get 6 minus these two combined is differentiating the z with respect to z variable, that's minus 1. And then moving on to move the first column over. And then we're still going to cross combine. There's no z here, and there's no x in here, so it's actually 0. The last component is the cross combine and subtract here. This will be this one combined with that one will give us 0. The partial derivative, this function has no x, so the derivative with respect to x equal to 0. That's negative x. Right. The first component is multiplication of x times y. Differentiating the y will give us 1, so it's 1 times x. That's the curl of the function. So in order to follow what's indicated by the Stokes theorem, we have to be calculate the normal vector of the plane. So what exactly is a plane? It's really the circulation is a square of size 7 center at the origin lying in the YZ plane. So the surface within this edge, within the square, is in the YZ plane. So you need to know the normal vector for the YZ plane. What exactly is the equation for the YZ plane? It's x equal to 0. So when x equal to 0, all the points in the YZ plane has x equal to 0. So that's the equation of the YZ plane. YZ plane. So the normal vector will be 1, 0, 0, 0. We were supposed to do a dot product between the two, so this vector dot this vector is what we have there. I did not, that's supposed to be the normal vector, but that's pretty much normal already. Normal vector is supposed to be a unit vector, so that's what happened here. So we've dot this vector with this vector. We end up getting, that was 5, right? 5 times 1, that's the only non-zero vector. So this calculation ended up getting us this. So after some classification, after simplifying, we have a double integral of 5, the curl dot n equal to a number 5. This is the vector. The curl of the vector field is vector, the end is vector, but the dot product between two vector is a number. So it's really a double integral 5 and then the s. Right, when the 5 to be outside is double integration ds. Double integration ds is typically the area calculation. So it's 5 times the area. Now we have an area of a square. The circulation around a square of size 7. Square of size 7, the area is 7 square. So it's really 7 square and then multiplied by 5. So the answer in the end, after figure out the curl dot n equal to a constant number, they become a double integral of a square integration region because we have a classical geometric shape which has an area that's pretty easy to calculate. We had a quick answer for the area computation. So it's the area times 5 times 49. That's number 12, the last question of the whole set. You might have a very similar scenario on your version. I'm not sure if you have the 5 though. So the 5 might be different. The square of side, the side number might not be 7, but it definitely should be something really similar to this question. And here I'm hoping that you understand the reasoning. Okay, we finish your version of it. Any question? That was an example applying Stokes theorem. The line integral itself shouldn't be too hard to calculate either because it's a square, right? Horizontal and vertical. When the horizontal, there's only one variable. It's probably in the YZ plane will be y-axis. And then the vertical one, then on the vertical horizontal one should be z equal to a constant number. The vertical one should be y equal to a constant number. In that case, if one number is constant, then the differential is equal. So it's not too hard to follow the circulation to calculate it, but the Stokes theorem is easier. The double integral is easier than the line integral. So I think both is fine. And you can check the equality of the two and check the how Stokes theorem apply to either situation. Another example I want to try to explain is question 10 in this sense. Right, this is applying Stokes theorem to find the circulation of F around a circle of radius 4, center at 9, 1, 7 in the plane d equal to 7. So because the plane, the surface is a plane d equal to 7. And we also see counterclockwise orientation, so we don't have to switch the orientation. We don't have to multiply -1 to our answer. The orientation is exactly the orientation in the Stokes theorem. The plane is the equation, d equal to 7 is a surface. So remember the Stokes theorem on the right side of the Stokes theorem is a surface integral. Knowing the equation of the surface, make the calculation of n. The n will be calculated, will be easier to identify. Other than that, according to the counterclockwise way, you still have to identify the proper curl. I'm not sure if it's constant. It would be nice if it is constant. And we have to work out the cross product. So let's see.
Okay.
Okay, so here we are. So let's see how it looks like with the curl. This is our vector. Then we're going to differentiate with respect to dx, dy, dz. But we're not doing a straightforward differentiation. We did a cross product version of it. So let's see, kernel of this vector is equal to this -2. Second one. I mean, we did a couple of times. I hope that with practice we get better at this. So it's -3 And then the last component, that was 0, that differentiation is -3. It's very familiar. So that's our curl, and then the surface is over here, so the normal vector of the surface will be 0, 0, 1. So when you cross product, this is equal to double integral of curl of the vector dot n ds. If we dot product of these two vectors, it will be -3. So it's equal to double integration -3 ds. So bring the -3 outside is double integration of ds, which again is area. This is area of a circle of radius 4. So the area is -3 times pi r squared. That's area of the circle. The r equal to 4, so it's -3 pi and then 4 squared. So that will be -48 pi. So that was question number 10. Hopefully, since we have a couple examples, I did very awkwardly, I did question 1 and 2. So try to practice the calculation part and finish some of the classical example on applying Stokes theorem. I hope that we were able to finish most of the assignment on 14.6. Moving back, let's look at a couple of questions for 14.5. The divergence and divergence theorem. Diverge of a vector is a calculation of a number that identifies the tendency of the vector field to go out, The divergence theorem is converting from a question of a double integration, converting a surface integral on a closed surface into a three-dimensional triple integration of the divergence of the vector field. So it was supposed to help with the computation burden. I don't think we had a lot of practice 14.5. Maybe we tried a few questions and maybe exercise a few on our own. The last question of this assignment are conceptual, just reviewing some of the idea that's been identified in the divergence theorem, right? The following true: if F is a vector field in three-dimensional space, W is a solid region with boundary S. Okay, so the surface integral S equal to the divergence. I think that's not true. The surface has to be a boundary. Solid region with boundary S, that's true. So the boundary is S, so W is a three-dimensional solid. So that's true. This is a divergence theorem statement. Number 2 is the surface integral on S is 12, S is a flat disk of area 4 pi, then divergence equal to 3 over pi. Depend on the divergence of the vectors. I think that should be false. Number 3, F is a vector field in three-dimensional space and then gradient of the divergence equal to 0. I know the divergence of the equal to 0. Let's see. We talk about that result, right? It was in the 14 point. It was in the 14.6 about the divergence of equal to 0. This question really. So true. I think that was false. This one.
Actually, it doesn't make any sense. Get it? Doesn't make any sense.
We can try it and see. Right, so we can try vector, see if that's true. If we see some of the very common scenario, if x equal to x, y, z. Okay, and then the divergence of f equal to 3, right? Derivative of x equal to 1, derivative of y equal to 1. So the gradient of the divergence of any vector is a single function. Gradient of this will be differentiating the function with respect to every variable. Probably pick out a wrong example. Just try to determine if this statement is correct. C x y and then y square and maybe z square. Try if that's the case. The divergence of any vector is differentiating the first component with respect to x, which we get y. Differentiating the second vector with respect to y, we get 2y. Differentiating the last one with respect to z, we get 2z. Okay, now we can calculate the gradient of this vector. Gradient means we find its partial derivative vector. Okay, so the gradient will be differentiating with respect to x, we get 0. Differentiating with respect to y, we get 3. With respect to z, we get 2. Gradient is not equal to 0 vectors. That's false. F is a vector field. So I'm trying to go through this quite conceptual. You can test it, try to say if every statement is correct. Satisfying divergence rule 1, and S is supposed to be the closer order to the outward than to the volume. Right, that's true. Basically, according to number 1, which is a divergence theorem, if the divergence equal to 1, that means this equal to 1. So then what we have on the right side of the equation will be the volume. And that should be true. The volume of the three-dimensional region enclosed by the surface. Last one, if F and G are vector fields such that they have equal divergence and F and G. That's not true. Divergence equal only means that outward flow tendency is the same. So divergence is summation of the partial derivative. It doesn't guarantee the irrational function are identical. So let's see. That was my question number 12. I'm not sure if you got identical. I'm hoping that this kind of gave you some indication what we're really talking about. The first question is a divergence theorem statement. Second question is about if the surface integral include the number, do we have direct answer to the divergence? The answer is no, we don't have direct relation between the two. And I tried the number 3. I get a counter example here showing that the gradient of the divergence is not going to be a vector, a 0 vector. Well, it's not guaranteed. It could be 0, but it could be not. Number 4 is a special case of the divergence there. If the divergence equal to 1, the right side equation is volume calculation. Because we can bring y to the outside. So triple integration dv, that's volume. The last one is comparing two vector. If their divergence equal to each other, that doesn't guarantee the vector field to each other. That was question number 12 on 14.5. If you're working on your version of it, there's also another version of this solution, 14.5 solution on there. So if you got a different version of it, you can try my version and this version to see if it covered all the questions you see on your assignment. So that's another. This is the one that actually applied divergence theorem to solve. We might have done this when we were working on the 14.5. But let's try it. Let me pull up one of the homework from the 14.5 so we can try it together. See if we did this one. Okay, so this is the question where we have a surface and x the boundary of D, and we're trying to find out the surface integral. According to the divergence theorem, the surface integral can be converted into a triple integral. And we have to find the divergence of it. Let's make something written down. If you have notes, you might have already calculated this one, but if you don't have notes, we'll work on it together. This is an exercise question for 14.5. We have a three-dimensional region D. The surface is this cylinder x squared plus z squared equal to 4. The y equal to 1 and y equal to 0. S is the boundary of the cylinder, is the of the boundary. So S is in the entire boundary, including the surface on the side and also the surface on the top and bottom, the boundary of the region. Therefore, this satisfies all the requirements for the divergence theorem. Now, what we need to calculate according to divergence theorem is equal to, that's what we need to calculate according to the divergence theorem, equal to a triple integral. Right, this is equal to triple integral divergence of f dv. Now the divergence is a single number, so it's a little bit better. We don't have to worry about like Stokes theorem. After we find curl, we have to find out the other lecture, and we have to identify the normal lecture of the surface. But in this case, all we have to do is find the divergence. It's a single function. And this is our vector. Divergence is differentiating every component with respect to the corresponding component. So x cubed differentiate with respect to x is 3x squared, cancel the 3, it's x squared, so it's x squared. Second component is y cubed, but you differentiate it with respect to y, you have 3y squared, but there's 1/3, so cancel the 3, and therefore, which would be y squared. The last one would be z squared. So that's what we're calculating. So then we will calculate, according to divergence theorem, we'll calculate this. So instead of calculating the original question, we calculate this because it's easier. So we were supposed to triple integration of x squared plus y squared with and then dv. And then how do we calculate this triple integral depending on the boundary. Now the boundary is bounded by the cylinder and y equal to 1, y equal to 0. So based on that, because it's cylindrical integration region, we will be doing a cylindrical coordinate. So x equal to, the radius is equal to 2, so x equal to, it's a triple integral, right? X equal to r cosine theta. Y equal to r sine theta, not the y, z. Z equal to r sine theta. And then there's y variable that's still y variable, so that's cylindrical coordinates. We're using r, theta, and y. Remember, cylindrical coordinate in the textbook is r, theta, and z, because we typically have x squared plus y squared, but here we have x squared plus z squared to do that. So this has a 4, that means radius equal to 2. So R is within the boundary 0 to 2. These boundary provided the boundary for Y. Y has integration region 0 and 1. And theta is a solid region bounded by the surface. So it's a whole cylinder. Theta is between 0 and 2 pi. It's a whole cylinder. Right, so these are going to be the integration limits, and we're integrating this one, and know that x squared plus z squared is x squared plus z squared here. So x squared plus z squared equal to x squared plus z squared equal to r squared. So we will have r squared plus y squared, and you can do dy, dr, d theta. Actually, it's r dr d theta, right? So cylinder, polar coordinate with cylindrical coordinate, so it's r dr d theta. y, and then r, b, r, b, theta. Integrating the y from 0 to 1, and then integrating r from 0 to 2, and then integrating 0 to 2. I'll let you finish the rest of the calculation because I feel like this is something we've done before. So, okay, the rest, you guys do the calculation today. Open the scanner already. The three of you that submitted the answer that was correct, thank you. So if you're still working on it, I'll let you finish the calculations. All right, let's go back to the calculation. That was this. So we're at so far, we analyze, we try to think about steps. And so step one, you write down the divergence theorem. Step two, if we apply divergence theorem, we have to identify the divergence. And then we now realize step three, we realize we have to do this calculation. And we have to, this is triple integral, we'll apply integration region to determine how we integrate this triple integral. So number 4, we analyze that. We end up doing the cylindrical component, we do a change of a variable. And then coming back here, step 5, we realize that we're also integrating that triple integral using this variable. These are the variable y, r, theta are what we're doing. It's a triple integration. That's why I didn't put a 2 there and replace r with 2 because this is now a surface integral. It's a 3-dimensional integration, so r has to be a variable form, not a number. I have to pace ourselves to not hastily change our variable to such a number, so we maintain those 3 variables. But r did have a boundary that r is from 0 to 2. Okay, lastly, you guys have to finish the computation for the triple integral. I'll leave you to finish the calculation.
I still haven't done writing down the
Okay,
step words.
we'll come back to that page. Right, thank you. That's right. Okay, thank you. We can actually finish the surface integral compare if the divergence theorem is correct. So if you're doing the surface integral, we will be doing 3 integration. On the top surface when y equals 1, at the bottom surface when y equals 0, at the side of the cylinder when x squared plus z squared equals 4. We have different normal vector. If you are finding the normal vector for y equals 1, it will be 0, 1, 0. But if you determine the normal vector, I mean f dot n, right? If you do the surface integral, you have to do the dot product. On the cylinder, it will be the normal vector will be 2x, comma 0, comma 2z. So the normal vector will be slightly more complex on the surface cylinder. And also to calculate a surface integral, your surface has to change accordingly. F dot n, because the f is complex vector field. The dot product with the normal vector on cylinder will be like a higher order polynomial. The double integral will be a little bit difficult to calculate. So this one is really preferred to apply the divergence theorem and calculate. Okay, so let me see how many of us has finished this. Let me try to see. Charles, your answer is not right. You might want to double check your calculation. I mean, every single time we integrate, we have to test our skill with higher level integrations and triple integral or double integral is a test of the order of operation and skill with integration. So when we're calculating, the first thing will be integrating the inner layer. If you integrate that, we have r squared y and then plus y squared, y cubed over 3. We're integrating the variable y. And we're going to put in the integration limit y equal to 0 and y equal to 1 if we finish the inner integration. The answer will be if y equal to 1, we'll have r squared plus 1/3. So that's what we have after we finishing the integration of the y variable. The second layer of the integration is integrating the r. Well, there's r dr. So we have multiplication of r dr. R's from 0 to 2. So the calculation, this, if you integrate it, r squared times r is r cubed. Integration r cubed will give us r to the power 4 over 4 plus 1/3 of r. That's 1/3, and you have r squared over 2. Those are the integration antiderivative for integration of r variable. Then we have r equal to 0 and r equal to 2. And that calculation will give us a number when r equal to 2 is 16. 2 to the power 4 16 divided by 4 is 4 plus 1/2 times 2 over, so that's 2 over 3. So that's the integration of dr. Lastly, we have d theta. We integrate 0 to 2 pi d theta. This is a constant number. You print outside of it. So it's 4 plus 2/3. This number multiplied by 2 pi. Let's try to make sense of this number. 4 plus 2/3 is 14 over. It's 14 over 3 times 2 pi. So final answer should be 28 over 3 times 5. This is my version of everything that we finish, including the setup and eventually finishing the triple integral. This is not the right way to present the triple integral, but I tend to lose sight of the focus. So I try to identify this is the focus. So I do that part only and finish that part now. And then we move on to the second layer of the integration. Once that one is finished, we move on to the third layer of the integration. So triple integrations, we actually integrated 3 different variables in that order. So dy first, and then dr, and d theta. It's not perfect as far as presentation, but it will be convenient to keep track of what's being done at hand and what will be done later. The inner layer is finished. Okay, hope that gives you some help as far as finishing up the calculation. Our final answer should be the 28 over 3 pi. Any questions? Okay, I assume that we have finished this one. Let's move on. Any question that we have? Yes. Done that one. Done that one. Back to 14.4 will be the search. We did that question. So now we triangle region. Let's try this question. And we may or may not have done this, but it's a surface integral that we we may have like practice of the S is representing surface with this parametric equation RUV. U is between -1 and 1, V is between 0 and 2. So we want to find the surface of S. So essentially, it's a surface calculation. I don't know if you remember how we do it. It's a past question. It was one of those questions that we did in 14.4. So to go back to 14.4, so how do we do surface integral? It depends on whether you have a vector field or you just have a function that you're integrating. So it's kind of two kind of integration question. One kind is when you already have a vector field and you want to find out the relation. So this is your vector field, and then you have a surface. So vector in relation of the vector with the surface here. So the vector dot the direction or the differential of your surface. You have to find the normal vector of your surface and do a dot product. And then dot product will causes us converting this to a double integral. So this is the kind of situation we don't have to multiply the derivative or the cross product, magnitude of cross product. This is the one you can directly find the normal vector of the surface and dot the F. And then the result will be in the double integral. Now, question number 2 also have a vector view. The kind of question that does not have a vector view is just the last two. Like we're integrating the y with that surface. This kind of a question is the dA is the surface integral differential, which should be yes. You have to find the cross product of RU and ER way. So this is the two that we are doing the surface integral directly with the surface integral differential. And that's what happened here. We are trying to find the surface area. It's kind of like a double integral 1 ds. But when you do that, you have to have the differential ds right out of it. It's really a surface area calculation. But the thing is, the surface is not a flat surface, it's not a circle, it's not a triangle or a rectangle. We don't have the easy formula for the surface area. That's why it will take several steps to understand this surface in order to calculate the surface area. So how do we calculate surface area? The notation is supposed to be like this. So 1 times ds. Okay, so we can certainly say that was just basically an area calculation. If we have a quick formula for the area calculation, which will be best, but right now we don't. So if we don't have the surface formula, how do we do it? And then we're creating those surface area formula because of this method. So we would multiply by the magnitude of RU cross RV on the partial derivative vector. You cross product these two vectors and then find the magnitude. Then EV. That's this. So there we have it. It looks like degree 1, degree 1, degree 1, degree 1, 2. They're all degree 1. So it looks like it would be a projection. You see, this is U from -1 to 1, V from 0 to 2. So on the UV plane, basically we're having this parametric equation. What is a parametric equation? It represents a surface, right? You have a UV plane, UV vector projected onto the X value, the Y value, the Z value. You're projecting from a 2-dimensional plane onto a 3-dimensional space. That's what this equation is giving us, a transformation from 2-dimension to 3-dimension. Okay. Of course, the X, Y, Z have their corresponding formula. That's X, that's Y, that's Z. So what are we? I'm just saying, from the double area, from the double integration perspective, that's a rectangle. So rectangle, and this is all linear. mean that we are looking at also a rectangle, but we don't know the size of that rectangle. So essentially, we could calculate this to identify this projection from this surface, right? It's a surface. The rectangle is a surface. Now, this is a three-dimensional surface, but it's like a rectangle in a different angle. So it may, the transformation or the projection may make this rectangle into a slightly bigger one or slightly smaller one. It all depends on this magnitude of this cross product. In the sense, the magnitude of cross product, it's like a, let's say, this is, I should write DA, right? I'll probably write it DA. I realize that it's a two-dimensional DA, two-dimensional. That's a surface integral, that's a two-dimensional integration, I should be using DA. So essentially, we're resizing the rectangle. So this is kind of like a conversion of the integration variable. The original one, you have the x, which supposed to be like the x dy. Right, except we don't know the boundary of the x and y. Over here, we're doing du dv. Right, if you're training the ds, which is the xy, to a du dv, you need a number multiplied, just like those r, dr, d theta. The r is the determinant of the Jacobian matrix. So that's really the determinant of the Jacobian matrix. Anyway, that's a bunch of geometric understanding of why do we calculate it this way. Let's look at the algebra. Right, so let's work on the calculation part. It shouldn't be too hard because the algebra one, we already have the r to calculate our partial derivative vector with respect to u. We're getting that it was a 1, and that's a 3. That is a 2. And we will find the partial derivative with respect to the v. So this is a 1. It's differentiating with respect to v. That was -1. That was 1. So that's a individual partial derivative vector. You probably should be able to calculate it by yourself if you want to. But if you do it with me, let me turn on the scanner. I mean, it's very possible that you are able to do this calculation. Start calculating it already. So I'll turn on the scanner just in case you are ready for your answer. Did you already calculate it? So if not, I'll calculate. Let's see. That was right. Thank you. So we will finish the cross product calculation. It's a cross product and then magnitude of cross product. So you can think of kind of like the determinant of the matrix if you focus on the calculation. But anyway, let's do the cross product. RU cross RV. You know how slow I am when I'm calculating cross product. So I think that you should be able to finish this a lot faster if you are familiar with the cross product calculations. We cross multiply and subtract. That's 3 plus 2. I get 5. Right. The second component, we're trying to move the column over and cross multiply and subtract. We get a 1. The last component, we cross multiply the first two columns. That's -1 minus 3. I get -4. If I'm not mistaken. So that was a cross product. But for the surface area calculation, we actually need magnitude of it. So it's double integration, and then this magnitude of this vector is root of 25 plus 1 plus 16. And then you have the u and v, right? But then where is u and v? Are we all the time? The v is 0 to 2. The u is -1 to 1. So you can see that was a constant number. It was 25 plus 16, 41, 42. So you have root of 42 there in that magnitude calculation. Then we have the double integration, and then there is the u dv. Remember where it was u was -1 to 1. Where was the v? V is 0 to 2. So you finish those integration. It will look like 1 minus -1, 2 minus 0, those are the integration. You do part by part. So you can see the final answer after you finish the calculation. So the main thing is knowing what to do with it. The calculation, if you look at detail, is not a lot of, computations. Just the idea of it, that was the harder part of the setting. So yeah, hard the calculation if you're trying to look at an overview of what's going on. That's right. Okay. So you see the calculation that was integrated, that would be 2. This is 1, right? Antiderivative is u, and u equal 1, u equal -1. 1 minus -1 is 2. And then you will bring the 2 outside. You integrate dv to 1 dv is v equal to 0. 2 minus 0 is also 2. And then you have this outside number 2. So root of 42 times 2 times 2. That was the answer. What if you are on the same page with me? Pretty much write it out. My calculation formula and the answer. So the answer should be C if you are calculating. So that was an exercise for surface area calculation using the parametric form. And anything else? That was a practice question from 14.4. And moving backward a little bit further, we have 14.2, where we would do 14.3, we'll do the grain theorem calculation. Let's see. The last question is. All right, the last question is to calculate this. We have this vector field. We're going to calculate the circulation of the vector field around the perimeter of the circle of radius 3. Now, this is really possible to just go ahead and do the calculation of the circulation. The line integral is you have a r. R will be a circle of radius 3. So r will be x equal to 3 cosine theta, y equal to 3 sine theta. So then your dr will be 3 cosine theta differentiated -3 sine theta, and then 3 cosine theta. And then d theta. So you will be integrating theta from 0 to pi, and then here is going to be 3y, y equal to 3 sine theta. So that's 3 times 3 sine theta. You dot product the derivative vector. So the calculation of the line integral circulation can be calculated directly. However, the question wants us to calculate using the Green theorem. We should find these two solutions very much identical. We will find the same answers. But what does Green theorem provide is a shortcut. It will make the calculation a lot more shorter. The line integral is not too bad to do either. The 14.2 and 14.3, many times the same calculation can be repeated using 2 different methods. You should be able to get the same answer. But number 1 is you got to understand what's Green's theorem exactly. Green's theorem is closely related to Stokes' theorem. If you remember what is Stokes' theorem, that will be Stokes' theorem saying that if you have a line integral calculation, you can convert that to a double integral. But it's a double integral of a surface integral calculation. But in Green's theorem, it's slightly easier because you only have 2 components to worry about. So the comparison of Green's theorem to Stokes' theorem is in Green's theorem, you only have 2 components, and therefore that's what we call vector M and N. So we don't have the P, the last vector, to worry about. So Stokes' theorem have a 3-dimensional vector field and a 3-dimensional line or curve. The vector field is circulated in that curve. But in the Green theorem, you have a 2-dimensional vector field and the 2-dimensional line or the curve C. Therefore, according to the Green theorem, what we have is circulation at dot dr It's the integration of this is a closed surface, a closed curve, closer. So this closed curve in the surface will include a region inside a closed circle. And this is a circle of radius 3. So then the double integral is what the area inside. In the middle, you're converting this to a double integral. Your integration region is exactly this integration inside. So we have this is equal to a double integral of integration of, we have the d and dx minus this n dm dy. I mean, how do we make sure we do the right thing? What I did is kind of like we did across combine and multiply. So you have m and n. How would we write dx and dy, right? And you would cross combine dn dx, dm dy. It's supposed to be a funny. Right, so that you know which one's supposed to be positive, which one is negative. The dn dx is on the positive diagonal. And also because the x is the first variable, you do it first, and then subtract the dn dy. And that's the dA. Right, so there's no worry about what was the normal vector that we're talking about. But in a sense, we are talking about the xy plane. They're all variable x, variable y is a circle in the xy plane. So therefore, on the xy plane, we have z equals 0 is the equation of the xy plane. So therefore, the normal vector, if you have to think about from the curl standpoint, normal vector will be 0, 0, 1. Okay, and then the curl of this vector will be this. This is the last component on the calculation of the curl, the z component. That will be the z component that we dot product. So then you pretty much this normal vector dot the curl of this vector, which will give you this. So there was no additional component to worry about. If it's a two-dimensional version of the Stokes theorem, you will be saying the Green theorem. So in part, we can connect the Green theorem to the Stokes theorem because the Stokes theorem is a three-dimensional version of the Green theorem. So anyway, we could calculate this by focusing on the other part. And we have our x m and we have our vector field. So we do dx d dy of our component. We have the first component is 3y. And second component is 6xy. So if we differentiate this one differentiated with like that one, first component differentiated with respect to x, we're getting 6y. The second component differentiated with respect to y, we have minus 3. 6y minus 3. So that's what we're integrating. And we're integrating on a circular region. This was originally the A, but since our integration region is a circle of radius 3, we converted it to a polar coordinate. So instead of doing the A, we're converting that to RdR, dr e theta. That's how we're going to do the A. And also on top of it, if we prefer to do polar coordinate, also convert this. So in the polar coordinate, what do we do? X is equal to R cosine theta, and then y equal to R sine theta. So the integration function will be 6 on sine theta minus 3 times R dr e theta. And we have the original variable in dA is dx dy. But with R dr d theta, R is the radius 3 circle, R is from 0 to 3, and theta is 0 to 2 pi. So these are the setting, and we have a polar component for the double integral. So that will be how we set it up for question number 8. I don't know if you were finished with 14.3 yet. I look up how much we've done. See, I don't want to. We can look at statistics of it, but I don't want to show individual students' answer. percentage. Average number of tags. Question 8. Okay, this is a question number 8. According to this data. So I guess it's not an overly difficult question if we don't to try it more than 2 times. So the rest of the calculations really finish the integration. It's kind of your calculation skill. Let me see if we have any new question for 14.3. We might have done all this question. Right, maybe we try this question as the last question of exercise for today. C is a closed curve consisting of a straight line segment from -1, 0 to 1, 0, and upper half of the unit circle back to -1, 0. So it's a closed curve to straight line and then half circle back to the original point. Using the Green's theorem to evaluate this is a closed curve integration. A line integral. So according to Green's theorem, we can calculate the partial to subtraction. And try it yourself. I wonder if you're able to calculate it without too much involvement on my side. So I turn on the scanner. Let's see how much we've done by ourselves. That was a question. It's a Green's theorem exercise. So according to Green's theorem, let me write it out. According to Green's theorem, if you have a m dx plus n dy, it will equal to, it's a line, I write it wrong. It's line integral on line C. It will equal to a double integral. Then D will be the region inside of C. Here we have dn dx minus dn dy. And this is actually dA, whichever you want to integrate. This we would definitely use a polar coordinate because the circular integration region is a half circle, right? Integration region goes like this. Starting from -1, 0, go all the way to 1, 0. And then go through a half circle back to -1, 0. So you can see it's a counterclockwise, definitely apply Green's. If it's a clockwise, you may have to add -1 to the answer. That's our calculation. So we will find the, so it's going to be a double integral. And the d and dy, this is our n. I'm going to find a derivative with respect to the y. It's the y, and there was a y. So we differentiate with respect dn m and dx. Okay, then still, this is going to be a 2y. This will be differentiating the x, right? It's going to be cosine x. So 2y plus 2y sine x. That's the dn dx. We minus the dn dy. dn dy be minus 2y cosine x is dn dy. And then dA. You see, if we finish the whole thing, we'll cancel the trig part. All we have to do is a double integral of 2y dA. Okay, and again, because of the half circles, and it's easier to do a polar coordinate, and in a polar coordinate version of x equal to r sine theta, y equal to r sine theta. So we do a polar coordinate conversion. The 2y become 2r sine theta. And then the dA in polar coordinate will be r d theta. Now we're done. Let's look at integration limit. It's a circle with radius 1. So r from 0 to 1. And it's half circle, so 0 to pi. So it's not 2 pi, it's 1 pi, 0 to 1 pi. Now we finish identifying the appropriate calculation. I assume that we are able to separate the variables and we will finish the calculation. Now we will integrate this theta 0 to pi sine theta, minus theta. And then the r is equal to 1 to r squared r. Let's see, if you already have the answer, let me see what was your answer. That's right. Thank you. You have your answer already recorded? Okay. Okay, thank you.
I'll just say like it's 12, it's 12:15 now.
Is that ready?
Yeah.
Okay, I'll let you know the answer. You guys already submitted a few, the final answer, due to the calculation should be A. Alright, so, don't check your calculation, there's a labor. We should do this integration, we should have the answer. That's it for today. The answer is A, you are still in the process.
With that
I
in.
think the one that submitted earlier. You gotta be excluded. Hi.
You are seeing this, is that actually handled by, that's Carol. Is that handled by?